as was said, I will be talking about Lagrangian fibrations, and that is by now a very old topic, I would say, but I think it's still very important, and it would be nice if more people would work on this subject, so I'm trying to advertise it a little bit, and I hope that works. So I'll be starting with, I guess, the most basic thing that you encounter when you study Lagrangian fibrations, which is Matsushita's theorem. So first of all, let me tell you what's a fibration. So f from x to b is a fibration. For me, that means that f is proper, a proper morphism, and f lower star of OX is OB. That, for example, that f has connected fibers, and that, what else? You can deduce from that that if x is normal, which is of course usually the case for us, then also b will be normal. All this is somewhat contained in the definition of what a fibration is. Then here is the informal Matsushita result, which says that any fibration of an IH as M, irreducible holomorphic symplectic manifold, is Lagrangian. So it's informal, so it's okay if it's not 100% correct. Any fibration means, of course, any non-trivial fibration, so different from the identity, different from the structure map to the point. And Lagrangian, well, I'll come to that later. Just think of it for the moment that the general fiber of such a morphism is Lagrangian. Lagrangian means that if you take the holomorphic symplectic 2 form and restrict to it, then this is 0. Okay. Right. So this is what Matsushita has proven. As I said, I will get to the details of that later. And let me give one example. Or maybe before I do that example. So what's the idea behind all that? For me, is the following. So if, here is my x, and here is my fibration from x to b. So so the reason for studying fibrations is somehow that x is a high-dimensional manifold, and they are of course complicated. And in some sense, you can reduce the problem of studying some high-dimensional object to studying some lower-dimensional object. So you have the fibers. This is not British. I'm sorry. And the base. So if you study fibrations, you want to know things about the fibers and about the base of such vibration. And the example, of course, is K3 surfaces. So if S is a K3 surface, and suppose we're given a vibration, so F S to be a vibration, and you can ask all those questions. So, for example, what about the fibers? So first of all, look at a general fiber. So if F and S is a general fiber, what do we know about that? Well, maybe I should have started by saying if that's a fibration, that's non-trivial. S has dimension 2, and there's not much choice for B. B has to be one-dimensional. And by what I said about normality, that means B is actually a smooth projective curve. It's a curve. So a general fiber is therefore also a curve. So what you can see immediately is you can compute the canonical divisor of F just by adjunction. That is canonical divisor plot of S plus F restricted to F. Canonical divisor of S is 0, F restricted to F is also 0, you can just deform it out. So this is 0, so you see that F is an elliptic curve. So we understand already the fibers quite well, at least the general fiber. Then there are also singular fibers. The way to see that is, you look at the Euler characteristic of a K3 surface. That is known to be equal to 24, which is what we have seen in the last talk, I think. And therefore, well, if you have a fibration over a curve where the fiber were all elliptic curves, and the Euler characteristic is multiplicative in smooth vibrations, so that will mean that the Euler characteristic of S is actually 0. So that's not the case. Therefore, there exist singular fibers. Okay, so they're classified by Kodaira. You know pretty much exactly how they look like. So there is, of course, this one. There is, I take 2 rational curves. So that's a nodal rational curve. That is well, the union of 2 rational curves intersecting as sketched. We can have cycles of rational curves of not really arbitrary lengths, but I think up to length 19. And then a whole zoo of other things, a cusp, a union with of 2 rational curves with a tangency of order 2, 3 lines, 3 rational curves meeting at a point, and many more. So singular fibers are classified, so we essentially know everything about fibers of vibrations of K3 surfaces. So what about the base? Well, let's look at so F upper star of omega B that embeds into omega S, the sheaf of differentials downstairs, the pullback embeds into sheaf of differentials upstairs. Yes. So if I look at H0 of that, so this is H0 of omega B. And then we also seen in Chiara's talk that this here is 0, so there are not so many curves that have no holomorphic differential forms. So this already implies that B is the projective line. So we know the fibers, we know the base. Are there more questions that we can ask? Yes, there are. So, if you have F as 51, then you can, for example, look at L, which is the pullback of O1. So pullback of an ample class from the base. Called L is first term class. Then you know that L squared is 0 because O1 squared is 0. And also L is Neff, it's a Neff class. Actually, I'm from Saxony, from Eastern Germany, and it's not true that in all of Germany. I might have to adapt. Let's see. Should I do? Yeah. Okay. Well, in Eastern Germany, one is accustomed to people from Western Germany telling you what is correct.
You should have went with Eastern German talk.
Daniel is also from Eastern Germany. Daniel.
I'm from Berlin. All right. So fibers base existence. So just told you what once you have such a vibration on the K3 surface, you get this isotropic class that is Neff. The converse is also true, so it's L in pick, or I want to call it H2 X Z H11 X. It's isotropic and Neff. Then you can show that the linear system actually defines a vibration.
S equal X. What's S?
Okay, the surface of the same one as defined here. Thanks. So much about existence. So the first thing you would do is you would look at Riemann-Roch. Riemann-Roch tells you that you have sections, and then you need to show that there is no base locus, and for this you need the Neffness. Okay. So much about existence. Another question that's interesting is deformations. So that's quite easy. So given F S to P1 and deformation S over some base we'll call that T. So the deformation of S, then F deforms with some vibration on this S here, F from curly S to T1 over T. If and only if T is contained in the Hodge locus. So T is equal to the Hodge locus of this class L, F upper star of O1 inside of T. Right, so the Hodge locus is the sublocus of T, where this class remains of type 1,1, and if they happen to be equal, so in other words, I mean that's a complicated way of saying that this class should remain of type 1,1 everywhere. Yeah.
Is S projective? Necessarily projective?
Doesn't matter. No, I think it doesn't matter for the moment.
So you can have a square zero class that gives you the elliptic vibration, but S is not projective.
Yes. All right. Then, of course, So much for that example. You get more complicated examples by doing what Chiara did. You take a K3 surface with a vibration. You look at the Hilbert scheme of that K3 surface. It maps to the Hilbert scheme of P1. And that is also a Lagrangian vibration. Yeah, okay.
Can I ask about this example? So, it's a consequence that the base P is smooth, or it's an assumption?
Well, in this case, it's a consequence because, as I said, part of the hypothesis of being a vibration tells you that if the total space is normal, then the base is normal. But a normal curve is so higher dimension. That's a problem. In dimension 2, that's one. All right. So here is Matsushita's theorem. Matsushita's theorem tells you the following. As I said, essentially what it says is that any vibration of an IHSM is a Lagrangian vibration. So let f from x to b be a vibration of an IHSMX onto a complex variety B, then the following hold. So, first of all, F is equidimensional. So, as always, X has dimension 2n. F is equidimensional, meaning all fibers have the same dimension. F is equidimensional, and every component of a fiber of F is a Lagrangian subvariety. Exactly. Be a non-trivial vibration, which is what Nicholas said. So E, it should not be it should not be an isomorphism, and E should not be a point.
It's not even rational. You don't want it rational.
Oh,
Really, you want
that's a good point. Yeah. Okay. Thanks. Bring the smaller than 2n in this topic. Yeah. Thanks. 2 is that B is a normal projective variety with only Q factorial or log-terminal singularities. Okay, if you're not familiar with these notions, then just ignore them. It tells you that there are two statements. There is a statement saying that singularities are not too bad. And the other statement is saying that B is projective. We just start with some complex variety, and we conclude that's actually a projective variety. Okay. So F is
With no algebra is the assumption on this.
no algebra is the assumption. F is locally, locally in D, projective, and smooth fibers are abelian varieties. Again, thanks for asking. There's no projectivity assumption on X. So we're in the weird situation that X might be non-projective, but both the base and the fibers are projective.
So what do you mean by locally projective? There is an algebraic structure on the
Locally analytically.
so yes.
Good point. So locally analytically in the small open neighborhood in the classical topology. Everything happens over the complexity. Okay?
But locally analytically, it is an analytization of some algebraic.
Well, let's not make it too complicated. You can embed into P to some power n times a small polygon. Okay. Or it says that B is Fano with Picard number 1. Call it Matsushita's theorem. I should say that so this part here, that's a very nice argument, which is actually due to Fairboson. So I think Matsushita just shows that the fibers are complex tori, but Boson gives an argument that they're actually algebraic.
It follows from being locally projected. It follows from the previous.
Well, okay, let me comment on it. So, yeah, but that was also not very much. Okay, sorry.
Yeah, but just formally. So
Yeah. So, right. So, Boson gave the argument for smooth fibers, and I observed that actually the same argument works for the singular fibers as well. And then it was Campana who thought that you get actually a little bit more than this projectivity in terms. Right. Yeah. So. Okay. So let me say something about the structure of the proof. I think so from the assumptions. What you should show first is that B is Morphism. I'll give definitions in a moment. So Morphism just means that it's well. So one way of saying it is that it's bimeromorphic to something projected.
And you'll give the definition of Lagrangian in the proof.
Yeah, let me first give this page with the structure of the proof, and then I'll give all the remaining definitions. So, from B being Morphism, you show that F is bimeromorphic to some F prime, X prime to B prime, where B prime is projective. Oh, sorry, that is an actual morphism here. Otherwise, that would be silly. And X prime is IH as M. All right, and then okay. So let me stop here for the moment, and let me go to the situation where I assume that the base B is actually Taylor. Or I could assume that B is projective right away. So the reason why I come with all these different assumptions is that there is some ambiguity in the literature as to the assumptions of that theorem. So sometimes B is assumed to be projective right away. Sometimes it's Taylor but smooth, projective but singular. And actually, I think you can get rid of all of those assumptions. Okay, so what would be the next thing that you prove? So if you know that you're Taylor or you're projective, then you can show that the general fiber of F is Lagrangian. And once you have that, you can show that F is equidimensional. So if you know that the general fiber is Lagrangian, then you can easily show that this Poisson statement holds, so that general fiber is abelian. And if you know that F is equidimensional, then you can show that F is locally projective. All right. Yeah, maybe I need a little more space now. So let's see. Yeah, definitely once you're here, you can show that. You can show that from the assumption of being Taylor or from the assumption of being projective. What other statements do we have? Equidimensional, that's done, okay. Yeah, okay, so I think one of the first things that you should show, even before that, sorry, let me insert another layer, is that the dimension of B is equal to n. And once you have that, you can show that the generic fiber is Lagrangian. You have rho B equal to 1. It also follows from here and from there. You have that B is Fano. Am I missing something? Q factorial nocturnal synchronics. Okay, that's well. Oh, sorry. So if you will, let me put that up here. So E has Q factorial and nocturnal singularities. You can show that either from being Taylor or from being projective. Of course, I should be a little more careful here. If you're Taylor, then you can only show that. So the same proof that would show that the Picard number is 1 would tell you here that the first Betti number is 1. So maybe this one either erase that or replace that statement by saying the first Betti number is 1, and then also the second Betti number is 1. And then. Okay, now somehow I have to come from the assumptions to all of these other conclusions. Namely, I'm missing the projectivity. And for the projectivity, that's a little tricky. You have to go down all that way until you see that F is equidimensional. Once you know that F is equidimensional, you can show that E is projective, and then you get that. Okay. At the hot summer afternoon, isn't that a wonderful diagram to scare people away? I hope I did not.
Also, you need to control singular fibers.
Singular fibers, I don't think so.
But then you see components of the fibers.
Good point. That is shown when one shows that F is equidimensional. So F is equidimensional. That's actually something that is not predictable. So plus all fiber components are Lagrangian. Okay. Yeah, I hope you can enjoy the diagram. So let me, on this board, fill in the missing definitions. So there, somebody was shouting Lagrangian. So
Sorry, Christian, but at which stage are you going to prove that B is scalar in the structure? Or is it clear it's clear?
well, I mean, as soon as you prove that it's projective, then it's scalar. Yeah, so when I start here, go down here and go up here, and I'm projective.
Okay.
So there's no linear proof of
I have fun. It's definitions.
So, but in the diagram, B projective also plus dimension B to N.
Come again, please.
In the diagram, so B is projective, also like plus dimension B to N.
So that's something that you can prove from it. So this arrow is supposed to pass through this. Everything's clear.
Right.
So that's, yeah.
The fact that it's projected by scalar doesn't mean that like all the arrows that start from there use an arrow that doesn't projected. Why do we need to pass by dimension?
You need to pass by dimension B equals N in both cases.
projective doesn't imply killer because projective is singular and killer is projective.
No. Both is supposed to be singular. So yeah, you can go like this. Just thought you were happy with the number of arrows. But feel free to ask me for more. I mean, I can still add a couple of them. So y and x is called Lagrangian. If the following holds, so take y tilde to y to x. That is a iota, a resolution of singularity. Then iota upper star of, for me it's sigma, is equal to 0, where h20 of x is c times sigma. Sigma is the holomorphic symplectic. Right, so you can, I mean, the only thing I want here is that this y is reduced. Otherwise, I cannot make much sense of that. I mean, you can either add the assumption that y is irreducible, or you say, well, a resolution of singularities includes the normalization that separates all the components. That is this plus it should be maximal with that property. So a dimension of y prime is equal to n for all y prime in y irreducible. So maximal with the property that the symplectic form then. Okay, that clarifies the question about being Lagrangian. Yes?
Are fibers known to be reduced or not? Are fibers with vibration of an antiquera known to be reduced?
No, that's false even for K3 surfaces. So the singular fibers of an elliptic K3 surface are in general not reduced.
Yeah, components are not reduced.
Oh, the component is not reduced, and also the fibers.
Okay. Can you have multiple fibers? That's one question.
Okay, that's not no.
Okay.
K3 surface we know that we can't, but in higher dimension, not no. So Moiseson, so B Moiseson, by definition means that there exists a B prime bimeromorphic to B with B prime projective. Okay. So were there other things which are undefined?
What is scalar singular array?
Scalar, that's a good question. Let me take a new ball for that. There's a quick way of defining what scalar is. So B is scalar. Definition: if a regular part is scalar in the ordinary sense, plus for all B in B, there exists, well, it's scalar with a scalar form omega, plus for all B in B, there exists a neighborhood U of little b, and an embedding U into some Cn such that, I'll say it, in an open in Cn, such that the form omega restricted to U is the restriction of the scalar form on B. So you have a scalar form on the smooth part, and then locally around the singular point, you can embed it, and it comes from restriction of the scalar form on some small open sequence. Are there other things that are undefined? Well, I will not speak about nocturnal singularities. Either you know it or not. In any case, we won't touch it. So EQ factorial just means that if whenever you have a Veil divisor, or B in B Veil divisor, there exists some M such that M times D, well, M different from 0, of course, is currently. Okay, I hope now everything is defined. Of course, we went in the details quite a bit, but what you should take away from this lecture is that, well, there is this observation about what we can show for fibrations of K-tree surfaces. And then, whenever you give yourself a fibration of an irreducible holomorphic symplectic manifold, with essentially zero assumptions, you can prove a bunch of things which are very close to what happens in the K-tree surface. Equidimensionality is, of course, trivial in the K-tree case, but being Lagrangian is also trivial. The base being projective, Fano is Picard number 1. Well, that is what P1 definitely is. And the fibers being appealing varieties, that is what elliptic curves definitely are. So we can imitate a large part of what we know in the surface case. And all the rest tells you that, I mean, these vibrations are actually very special, very, very well behaved. So if you really got lost in the details, then please take this as a message. So just having a vibration puts huge restrictions on the geometry of the varieties. Let's see what we can prove. So, I mean, a large part of the proof is actually using the Holomorphic Symplectic form. So, reminder, BEF form, most of it is what Gerda already said. So, Q from H2 of X, that the integers is non-degenerate quadratic form. Signature is 3 comma something, 2 minus 3. What else do we have? We have that, so it is well behaved with respect to the Hodge decomposition. If I take the H20 plus the H02, the orthogonal complement to that is the H11. Of course, here all the time I extend scalars from the integers to the reals, from the integers to the complex numbers, and so on without saying. What else do we have? We have that Q is positive on H20 plus H02, the underlying real space. So H20 plus H02 is defined over the reals because it's invariant under the complex conjugation, and on on the chemical. Another thing that Chiara mentioned was Q of alpha to the power n is up to some constant integral over alpha to the power 2n. Okay, what else would I be needing? Yeah, so, okay, so from this it actually follows that let's take Q on H11, then it has signature 1, comma, 22 minus 3. Also said that. H11. And then let's see what we can do. Oh, I think there's one more thing. Let me see, does that follow from here? So, I don't think so. So, one more thing which I think we had not seen before is that if you have L different from 0, but Q of L being equal to 0, then L to the n is different from 0, but L to the n plus 1 is equal to 0. By this I mean the n-fold self-cup product. Right? So this lives in H2n. This lives in H2n plus 2. So that's a very strong statement. If you have a class and you don't know anything about it, then well, as soon as it's non-zero, you see that the nth power of it in H2n is also non-zero. Very strong. Okay. Well, that's all I'll do. Let's see.
Is the last claim obvious?
One minute.
So how do you see this?
That L to the n is different from 0 is actually not obvious. It is it's a theorem of Verbitsky. I don't remember if there is it might also follow from, I mean, there are a lot of formulas for this quadratic form Q. I'm not so sure, maybe it follows from one of these formulas.
And the n plus first power, you see this one, not the higher one, which is here.
I think that L to the n plus 1 is 0. That is not so difficult to see. You would need to know, I think you'd need to know that the pairing of L with a Keller form is non-zero. And once you have that, you do something like you put you apply Q to T times L plus a Keller form where T is a variable, and then you evaluate the Hodge relation, this one here. Then you see that on the left side you only get powers of T up to the order n. On the right hand side you have also higher powers, but well, so then you conclude that the higher powers on the right hand side are 0. The coefficients have to be 0, so L to the n plus 1. Okay. Let me prove. And you see, much of that will now be quite easy. So prove if E is scalar or projective, then the dimension of E is equal to. That's the first thing we want to prove. And this now follows just from this last property. So take L, which is F upper star of the scalar class. Well, we know that F upper star is injective, so F upper star of a scalar class is certainly different from 0. You can, of course, also take, in the projective case, F upper star of an ample class. So this L is non-zero, and Q of L to the n is equal to the integral over L to the 2n up to some constant. But this is the integral over x, cx, f upper star of something to the 2n. And this something to the 2n, so the scalar class to the 2n, this is certainly 0 because the dimension of P was supposed to be strictly smaller than 2n. So this is 0. Well, therefore, you see that L to the n is non-zero, but L to the n plus 1 is equal to 0. But if I have a scalar or an ample class, then its top exterior power is always a volume form. So the volume form is non-zero, so this is the highest power that I can take until I get something that is non-zero. Then you see that the only choice is dimension of P. Okay. So in other words, the pullback of the class behaves as if it came from something n-dimensional, and well, as it was scalar or ample, the base must be n-dimensional. All right, so this is already this first step. So you see, it's just a little bit of yoga with the Holomorphic form. Second step is actually the same. So if you want to show that so if we want to show that the generic fiber of F is Lagrangian. So let's call F this generic fiber. And by Hodge theory, it suffices to show the following integral values. Integral over F, sigma with sigma bar, which omega to the, or whatever, right. Oh, I see. So this would be n minus 2 here, because at this point I already know that the dimension of F is equal to n by step 1. Right? So I want to show that the restriction of the symplectic form to the fiber is 0. And I claim that for this it suffices to show that sigma wedge sigma bar, and then you fill up with a scalar class, integrated over F is equal to 0. That's just by Hodge theory, because that is, on the primitive homology of F, this is the metric, so to speak, evaluated on sigma. So that is positive definite. And therefore, if that is 0, then also sigma has to be 0.
is omega.
Omega is a killer class. So sigma is on the symplectic form, and omega is a killer class. And of course, I think of all of them as being restricted to. Okay, and for this, I can do just another computation with the PDF form. So you consider, this goes a little bit in the direction of your question from before. I consider Q evaluated at sigma plus sigma bar plus T times omega plus S times L, where L is F upper star of a Killing class. Right? And then what I want to do is I want to raise this to the nth power, and then in the end I would like to use the Fujita relation. So that is of course Cx times the integral over x. And then here I have well, sigma plus sigma bar plus t times omega plus s times L to the 2n.
Okay, I think I have a question about the structure of this proof. Why are we proving this if we have to prove it also for this to close, we have to prove it anyway from different assumptions, right?
Sorry, come again, please.
We will have to prove this fact also from different assumptions.
So so here we've seen that step.
Yes.
Now I'm talking about this step.
Yes, but to get to this
Yeah.
we need to know the generic fibers of F are Lagrangian anyway, right?
Sorry.
If I get this correctly, to get to this step, we need to get through this anyway, right?
I got the question. So we're showing. So
we're showing
that the general fiber of F is Lagrangian. That's what we're doing.
We are showing it, assuming that V is projective. But to get that V is projective, we need to show it anyway.
We need to follow the flowchart. Yes.
So we will have to show it anyway from different assumptions. I don't understand.
I'm not so sure what. So this was step one, and here we're. So this is step two. Okay. I didn't copy the assumptions.
Yes. Okay.
But the diagrams you can say.
Yes. To prove that V is projective, we need to prove the F equivalent, and to this we need to prove that the generic fiber of F is Lagrangian.
To be a tree.
Something is wrong here.
So
we have somehow to start from the hypothesis on the left. Otherwise, on the different cycle.
From this assumption,
we get that
I get here.
And we need to get here to prove that V is projective in the first case. But now we're proving this from the fact that V is projective.
So what I'm saying is, once we have this, we can go there, regardless of this stuff. And then we go down, and then we go up.
But we are assuming that V is projective on the top of the other step.
Yes.
Yeah, because here we're in step one.
So this step
one.
so step two is unnecessary?
Okay, I think the confusion is just where we're starting.
No, okay.
I'm
not sure if this diagram is cross. That's my
Okay, let's discuss the diagram later on. Let's do step 2, okay? So I have this equality here, and I treat the left-hand side. So on the left-hand side, you see, so these here are 2, 0 and 0, 2 form, and both of them are 1, 1 forms. So the left-hand side is actually equal to Q of sigma plus sigma bar plus 2 times S times T times Q of omega comma L plus T squared of Q of omega to the n. You agree? Q of L is equal to 0. That's why there's no S squared Q of L here. Okay, and the right-hand side, oh, I think I don't want to do that. Okay, so the point is now you consider, so look at the coefficient at, let's see, where do I want to get? Look at the coefficient of S to the n times T to the n minus 2. So on the right-hand side, this is proportional to n powers of L, n minus 2 powers of omega, and then I have sigma wedge sigma bar. So this is the integral over x, sigma wedge sigma bar, wedge omega to the n minus 2, wedge L to the n. Okay? And this is some constant times the integral over f, sigma wedge sigma bar, wedge omega to the n minus 2. So this is exactly what we want to manage. Okay? So the point is that if I take L to the n, E is n-dimensional. So this is a volume form downstairs. So it's some non-zero multiple of the class of a point. So this pullback is then the non-zero multiple of the class of a fiber. So in the left-hand side, I'll try to. We have to try to get S to the n times T to the n minus 2. So we can only get S to the n if we take this term to the n. If we take this term to the n, then we also have T to the n. Then we're already too high in powers of T. So this coefficient is equal to 0. And put the two together, and this proves step number 2. All right, and I give my time's up for today. So I'll be happy to discuss the diagram with you. It might be that you're right. I haven't understood what the problem is, but you'll tell me. In any case, I think the proof is fine. So everyone has to piece it together differently, but I think the proof is fine. Step 1 and step 2 is okay. We will do tomorrow this arrow, and we will show this arrow so that the general fiber is abelian. And then maybe I'll also prove that the power rank is 1 with the projective. And in the end, I'll say some words to how to get to the actual.
I think that maybe it's enough just to ignore the arrow that goes from projective to Euler, and then everything goes.
The one who made you right, you can erase it.
Yeah.
Sorry, come again?
The one from B projective to B scalar. If you just ignore that one, then everything goes so nicely.
Okay. I have no idea
But
why.
you start
why
with
that is a good
scalar and
idea,
then.
but,
You don't want to have a cycle of your proof, right?
it's a bit of a cycle.
No, it's a fine because you still have from B projective to dimensional P equivalent, but you also have the other way, so it's fine.
That's way above my head. But I'll be happy to answer questions that I can actually answer. But